always been a need of reliable technology for developing real-time applications in biomedical field. Through this project, we made an effort to take a positive step towards it. Hello and welcome. We are Team 46-5 from National Institute of Technology, Karnataka, Surathkal, and we are here to demonstrate our project for the TI India Analog Design Contest 2012-2013. Our project is an optimized low-cost pulse oximeter which can be used for remote patient monitoring. Pulse oximeter is a medical instrument for measuring the blood oxygen saturation non-invasively and continuously. It does this by shining lights on any peripheral body parts such as fingers, earlobes, toes, etc. By measuring the absorbance of the infrared and the visible light by the blood after being reflected by the body tissues, it can determine blood oxygen saturation and heart rate. The output of the pulse oximeter is called photolithosomograph or the PPG. It contains the information about heart rate and oxygen saturation. Our device will extract this information and deliver results in real time through a wireless mode. Our system is divided into two modules, the analog front end and the microcontroller module. The analog front end starts with the probe. The probe we have used is a Nelcor DS100A probe. It consists of two LEDs of different wavelengths. One is the infrared LED of wavelength around 650 nanometers and one is a visible LED of wavelength around 940 nanometers. There is also a photodiode which is connected opposite facing two LEDs. The LEDs in the probe are driven by an HBH based LED driver circuit. We have used BJT transistors to implement this circuit. The current flowing through the LEDs is of the order of few tens of milliamperes. Also, the intensity of the LEDs in the probe is controlled by the DAC output of the microcontroller pin. The range of operation of the DACR is from 0.7 to 1 volt. The output of the photodiode is of the order of few microamperes. Now this output is amplified by a transimpedance amplifier which is built around using LM392 op-amp. We put a feedback resistance of 1 mega ohm. Now we chose LM392 op-amp because the output current of the photodiode is very small and it has a very low diff current. The output of the transimpedance amplifier is around 8 to 12 millivolt AC signal plus some DC offset. Now from this stage onwards we begin a filtering process. Now this output of the transimpedance amplifier is fed into a unity gain active second order Butterworth low pass filter. This offers an attenuation of 40 dB at 50 Hz. This eliminates most of the ambient noise due to ambient light. Now the output of the second order low pass filter is a PPG waveform which has a very small AC signal around 8 to 10 millivolt and plus some DC offset. Now in order to amplify this AC signal we have to eliminate the DC component. For that we use a simple first order RC high pass filter which eliminates the DC components. The cutoff frequency of this is 2.5 Hz. Now this band pass stage is repeated once again for further filtering the signal. The output obtained after the two-stage band pass circuit is an AC signal of amplitude around 8 to 10 millivolts. Now this is amplified by using a non-inverting amplifier of gain approximately 50. Now which makes the amplitude of our AC signal to around 400 millivolts peak to peak. Now since we have to sample this AC signal, we have to shift this to a certain positive level. So for that we use an adder circuit which adds around 1.2 volts to our waveform. Now the output of this adder circuit is a PPG waveform which can be utilized for calculation of results. The output PPG waveform from the analog front-end module is fed into three microcontrollers. The first one is the MSP430 FG439. The second one is the MSP430 F2274 on the EZ430 RF2500 target board. And the third one is an MSP430 G2553 on the MSP430 launchpad. Considering the first microcontroller, the MSP430 FG439, in which the timer is running on a clock that utilizes a 32 kHz external crystal for its operation. Now the 12-bit ADC of this microcontroller is configured to sample in a single channel repeat sequence mode. The sampling is triggered by the timer interrupt. The sampling rate achieved is 100 samples per second. For this we have set the timer A, the 16-bit timer, to operate in the up mode and which generates interrupt every 10 milliseconds. Now on this microcontroller we have two algorithms running. The first one is the peak detection algorithm which computes the heart rate and the second one computes the oxygen saturation. The results obtained can be displayed on an LCD module. The LCD module utilized is the SB-LCD A4. To establish the wireless communication, we are using the EZ430 RF2500 from Texas Instruments. This has two identical target boards, one of which can act as an access point or the receiver, and the other one can act as an end device or a transmitter. Each of the target boards comprise of an MSP430 F2274 microcontroller and a CC2500 2.4 GHz wireless transceiver. Both the target boards communicate with each other using the Simplicity TI protocol in a simple peer-to-peer fashion. Now coming to the microcontroller on the transmitter side, which takes as input the PPG waveform from the analog module. The ADC is configured in a single channel repeat sequence mode. The sampling is triggered at every timer interrupt and the timer generates an interrupt at every 25 milliseconds. Now the transmitter sends a sampled value of the signal every 25 milliseconds to the receiver, which is in connection with any remote PC. Now coming to the receiver part, the receiver communicates with MATLAB serially at 9600 baud rate. It sends the sampled signals obtained to MATLAB, which the MATLAB uses a function to plot those signals and display the PPG waveform. A more cost-effective solution to convey the end result to the user is achieved using an MSP430 launchpad, which has an MSP430 G2553 running on it. The MSP430 G2553 or the MSP430 launchpad has its timer running on A clock, which utilizes a 32 kHz external crystal for its operation. Now the microcontroller takes as input the PPG waveform into one of its ADC channels, which is configured in single channel repeat sequence mode. The sampling is triggered at every timer interrupt and the timer interrupt is generated every 25 milliseconds. Now the samples obtained are sent to MATLAB using serial communication via the back channel application UART. Now the MATLAB uses these samples to display the PPG waveform. Now we shall be showing you the demonstration. Our device operates in two modes, the heartbeat mode and the SpO2 mode. So we have kept this switch for the user to switch between any of the two modes depending on whether he wants to see his heartbeat or oxygen saturation. Now first we shall be operating our device in the heartbeat mode. Now as the probe is worn, you can see the PPG waveform being displayed on the oscilloscope. Now after the computations on the microcontroller, we can view the heartbeat on the LCD module. The H here represents the heartbeat. Now we shall switch the operation of our device to the SpO2 mode. In the SpO2 mode, the two LEDs are multiplexed at 10 seconds. As you can see, at the end of 10 seconds, there is a switching between the two LEDs. After the computations on the microcontroller, we can view the result on the LCD module. The S here represents the SpO2. Now we shall be showing you the wireless transmission of data. For this we have utilized an EZ430 RF2500 from Texas Instruments. The sample values of the PPG signal are being transmitted wirelessly to a remote receiver using Simplicity TI protocol. For the demonstration purposes, we have kept a remote receiver, which is a EZ430 RF2500 connected to a PC. Now when the user sends a request to MATLAB to display the waveform is being displayed for the last 15 seconds from sending the request. Now we will be using a more cost-effective solution to display the PPG waveform on PC. So we will be using an MSP430 launchpad, which communicates with MATLAB using the back channel application UART. Now when I send a request to MATLAB to display the PPG waveform, the MATLAB is able to display the PPG waveform on the basis of the samples collected in the last 5 seconds.